We're back with phased array antenna trainer PAT20. I'll show you the operation of the instrument. The instrument has a 16:2 LCD display which is displaying the frequency as 1850 MHz right now. The memory location is 1, which can be from 1 to 1000. M stands for manual mode of operation, and 110 dB is the 110 dB microvolts of output available at these outputs. This particular output will give a frequency from 899 to 2000 MHz. This one will give a frequency output from 87 to 898 MHz, and another one will give output of 5 to 86 MHz. This particular RF output is common. This particular cable will have to be connected to this input if the output needs to be from 899 to 2000 MHz, and the same cable has to be connected from this to this input. On selection of the particular frequency, the corresponding LED will light up so that there is no error in operation. Right now 1850 MHz is being selected, so this particular LED is glowing, indicating that we need to connect this cable here. The menu button, when we press, we can select the memory location as 1 to 2 to 1000 MHz. Different frequencies can be stored at different memory locations for easy recall. The operation can be selected from manual to auto mode. Right now manual is being selected. Auto will be used to give a trigger to the receiver for automatic plotting of the frequency versus gain plots. The step can be selected as 1 MHz, 10 MHz, 100 MHz, 50 kHz, or 0.1 MHz or 250 kHz. Right now 1 MHz has been selected. Now if 1 MHz has been selected, then pressing up or down will increment or decrement the frequency in corresponding step sizes. Because the PLL synthesizer has been used, the frequency is accurate to within few kilohertz, so there is no drift of the frequency. This completes the operation of the instrument. This asterisk right now is being displayed, which indicates that the PLL is in lock right now and the frequency is not drifting. It also has a trigger out which can be used to connect to the receivers. A mic input is provided which can be used for transmitting of voice data over a RF link. The modulation can be set from FM to CW. On selecting to FM, the source of the modulation can be either mic or internal 1 kHz tone generated, and the modulation deviation can be adjusted continuously by the use of this control. For normal operation, we are going to use CW as the modulation. 20 dB pad is connected built in. The cable used is RG316, which is a Teflon dielectric silver plated conductors, which has a very high isolation. The operation is similar for the receiver as well. The right now display is in resolution of 0.1 dB. Upon selection of pressing of menu, we can select different memory locations, which can be from 1 to 1000. Different frequencies can be stored for easy recall. Upon pressing menu button, again this M is blinking, which can be selected from A standing for auto and M standing for manual. Upon setting for it in auto mode, we press enter key and auto is being selected, and auto A is being blinking right now, indicating that the receiver is waiting for the trigger input at its 2 BNCs. Upon receiving a TTL trigger pulse at the stepper input, the receiver will advance to the next memory location without changing the frequency, and it will record the level data at the instance of the trigger input, indicating that the motor has rotated in that step increment and it needs to store the level of the received signal strength. Hence, if we connect the stepper motor controller trigger output, as we see, via a BNC cable to the trigger input of the stepper, upon automatic rotation of the stepper motor controller, I'll show you briefly how it operates. If we select the step size of the stepper motor controller as 5 degrees and set S standing for slow, CW standing for clockwise mode of rotation. If we set the stepper motor controller into an auto mode, we press enter. Now this stepper starts incrementing the motor in steps of 5 degrees and it shows the current position. Correspondingly, upon reaching each step locations, a trigger pulse is generated which is fed to the stepper, which allows the stepper to increment its memory location and record the level data at that instance. So upon 360-degree rotation of the motor, 72 pulses will be received and 72 memory location data will be filled at the same 1850 megahertz of frequency. That memory location data has to be noted down because that location data will be used at the time when we are plotting the data in the computer software. The computer software will require the location data to be filled in. Right now it is 1 to 72, so we will use the same data to plot the antenna. Now I'll try to connect. Now you see this antenna is right now being rotated in steps of 5 degrees. We need to make sure that these cables are not entangled after rotation of 360 degrees. We need to provide sufficient room for the cable to rotate since we are not using a rotary joint, and we need to unscrew the cable and screw it back on again so as to safeguard and increase the life of the cable. I'll try to plot the antenna pattern in 360 degrees once again and show you how the plot comes out.